Up next, I would love to introduce, Caitlyn Lewis, who's the research director at the LEV Foundation.
Okay, hi everybody. My name is Caitlyn. I am the research director at the Longevity Escape Velocity Foundation, and I'm going to walk you through how we are going about identifying therapeutics for damage repair, starting in mice, but with profound implications for humans. So since normally I would be speaking at aging conferences, and this is not that, so some of you might not be quite as familiar, but aging actually kills 100,000 people every single day. So it is by far the most impactful cause of human suffering and mortality, and yet we don't treat it like a disease. It is responsible for more than 90% of deaths in high-income countries, but it's also incredibly expensive. So the global cost of treating age-related conditions tops $1.3 trillion, or $1.8 trillion annually. And so this is no small number. There are a lot of people interested in trying to fix this, something that pharma could perhaps get behind. So this is the framework that is the kind of the foundational frame, I guess, that underpins everything that we're doing at Longevity Escape Velocity Foundation. It's the damage repair framework. It's sometimes referred to as the SENS paradigm. And essentially, the core idea is simple. Aging itself is not that mysterious. We've known what causes a lot of these things for a really long time. It's the result of the accumulation of specific types of cellular and molecular damage that accumulate and ultimately manifest as diseases. But the difference is most traditional approaches are focused on trying to slow aging down, and instead we look at this and we think, okay, well, what is something that we can do to reverse the present condition and restore it to its normal function? And so this framework that was conceptualized in the mid-2000s by our founder, Aubrai, it's elegant because it makes aging actionable. There is something that we can do about each of these things. And it's more of an engineering problem than it is a biological one. So an analogy that some people really dislike but often gets used in my field is you think about a rusty car, an old car that breaks. Now, cars weren't designed to run for 100 years or more. They're designed to run for 5, 10, 20 years, maybe at most. But yet we can keep cars in pristine condition by restoring them. If you have rust on the car, you don't slow down how quickly rust accumulates. You restore it. And so aging similarly should be addressed in the same way. This is by repair and not with resignation. So to do this experimentally, we have built RMR. This stands for Robust Mouse Rejuvenation, and it is our primary experimental pipeline. And the goal is to test multiple damage repair aging interventions in mice simultaneously. So we think we need to do this to reflect the natural complexity that exists within aging, but this also should mean that our findings are more reproducible, more relevant, and hopefully also translatable to humans, which is where it ultimately matters. So we want to move from isolated interventions into complete, more rejuvenation strategies that we can see move into the clinic. Our first study recently completed, we did 1,000 animals. This was like the largest scale mouse study that had been done to date. And it was really just to prove a point, although we got a lot of insight from it as well. But addressing the rhetorical aspect for policymakers and funding bodies and other academics even, is this possible? Can you rejuvenate mice? Well, the answer is yes. But also from a practical perspective, what are the kinds of things that are really needed to get this job done? And so it showed pretty clearly to us that we need more than a single intervention in basically every single case. And we also can't be including interventions that are absolutely impossible at the scale of humans, like something called parabiosis, which is effectively surgically fusing the circulatory systems of old and young mice. Like, I don't see that as something that's going to be moving into humans anytime soon. So it had to be practical. We had to develop a short list of interventions that fit these criteria in order to do this, and in the process, RAID was created, the Rodent Aging Interventions Database, that it has, basically it's a compendium of all of the studies that have been done according to the specifications that we use for our studies. So if it has to be damage repair, it has to be initiated when mice are already old, because otherwise you're not really fixing anything, you're preventing it. A number of criteria like this. And you can see from the visual that the results were shockingly few. There were not very many, at least a year and a half ago, not very many interventions which had rigorously been tested in this way. Fortunately, that has since changed. But nonetheless, building this really helped us to prioritize high-impact interventions where we had the confidence to say that this was more than just hype and sufficient to include in a $3.5 million study. So, and importantly, this remains a living resource. It exists on our website. Anybody can use and access it. I'm not going to go through all the specs. This is also publicly available, but all in all, 1,000 animals, 37 intervention groups with all of the controls and everything, and sampled across multiple different time points. So it got messy pretty quickly, but I think that chaos is probably representative of what we would see in aging anyway. We also had a cross-sectional design, so we're tracking animals across time points when they're not apparently ill yet. Operationally, it looks something like this. This is not even any of the data from it. It's just all the different groups, but we will be replicating this in our next study, which I'll get into in a minute. But the key insights from this were essentially, is the study feasible? Or is combining interventions feasible? The answer is yes. So we've known for a long time that aging results from multiple different types of damage, but what we didn't know is whether or not stacking interventions on top of each other would have unintended consequences in terms of stress or other problems they might cause. So fortunately, we didn't observe that, and we do think that things can be safely co-administered and have an effect. We did see health improvements in our animals, and then it also helped us to lay the foundation for our next big study, which Aubrai has since decided to double in scale. So it's 2,000 animals. There will be 20 actual intervention arms, but probably more like 70 intervention groups with all the controls. And again, looking for synergies between things. Because the data set is much larger, this also demands that we have more advanced analytics. I think Aubrai is one of the things that we're really looking forward to for that, but this is also with other ML platforms and utilizing multi-omics data and then feeding that into something like Aubrai the Agent, which can then distill it down for us. And so we will, at baseline, include rapamycin for all the animals. It's an mTOR inhibitor. It's one of the oldest longevity interventions, and it's still kind of the gold standard. So it's pretty boring. I don't like that we have to use it, but you really can't argue that anything is better unless it's absolutely blowing the gold standard out of the water. So we include that. We also include exercise wheels for everyone. I learned that in America, it's not considered standard necessity for animals to have access to running wheels. In the EU, that's different. So they'll have all of those, but also we have 8 brand new interventions that are each targeting different types of damage. So for example, deuterated fatty acids. In normal cell membranes, the lipids that form the membrane are really highly susceptible to oxidation or lipid peroxidation, and then this kicks off a cascade that then damages mitochondria, damages proteins and the genome and other cell membranes, ultimately causes cell death. What we know is that by providing deuterium-reinforced fatty acids, which is where some of the hydrogens specifically are substituted with a heavy isotope of hydrogen, deuterium. These are physically resistant to this process, and so will prevent this cascade from progressing. And so in this way, you can protect against membrane damage even in conditions of oxidative stress. Also things like exosomes, which a lot of you have probably heard of. It's typically in the context of cosmeceuticals, but I think that's probably mostly for regulatory reasons. But these are small vesicles that a number of different types of cells will secrete, and they're important in intracellular communication, which breaks down during aging. So in many contexts, exosomes are thought of as being restorative for that normal communication process. IL-11 inhibition, so IL-11 is an inflammatory cytokine. It's a primary component of something called the SASP, senescence-associated secretory phenotype, which senescent cells kind of spit out all the time, and it's very bad for you. And so we know that IL-11 is grossly upregulated with aging, and that dampening it allows for tissue regeneration and prevents a lot of the fibrosis and problems that will occur otherwise because of aging. Also, a novel senolytic. It's not ours, it's a collaborator's, but it's proprietary, so I can't talk that much about it, but we are excited to include it in the study. Oxytocin is kind of a fun one. Most of us think about oxytocin as it's like the cuddle hormone or love hormone because of its association with pair bonding and orgasms and all the fun things. And it turns out that it also has some really important regenerative properties for specific organs and tissues. And so, and it declines during aging. And so restoring that normal physiologic kind of peripheral circulating oxytocin levels is shown to rejuvenate the specific tissues that are affected. So we'll be including that. And also interesting is albumin. Albumin is by far the most abundant protein in the serum, and it's responsible for basically binding to and detoxifying oxidized products, damaged proteins from the blood. The problem is that as we age, albumin itself becomes oxidized, and it starts to get really bad at doing its job. And so I believe that by replacing with kind of young, fresh serum albumin, that it will help restore this natural buffering capacity. And as a bonus, like plasmapheresis already exists, that those machines are approved, people get it for various conditions, and so the regulatory hurdles for something like that are probably pretty minimal. Partial reprogramming, a lot of people have probably heard of. It tends to confuse people, but you're basically restoring a more youthful gene expression profile without making cells go all the way back to when they were stem cells, so they start acting like they're younger again. And CDC42 is it's a signaling molecule that primarily affects hematopoietic stem cells and other stem cells, but it becomes really strongly overexpressed or hyperactivated with aging. And so studies shown that if we can dampen this, then you kind of restore the normal niche behavior in the stem cell compartment. So with all of these put together, like this is definitely a multi-pronged approach. Interventions aren't going to act in isolation. So we think this is actually really exciting when we take things that directly maybe impact different markers of aging or different causes of aging, but indirectly they converge on the same pathways. We think that there's probably a lot of synergy to see there. So this is about more than mice, of course. We can have the world's longest mouse and nobody is going to care. Ultimately, we want to see these things moving into the clinic, and that happens with a really careful biomarker collection and tissue banking and planning for clinical stages later on. If you haven't heard of longevity escape velocity, it's the concept that our organization was named after, and it's effectively if you can undo more than a year's worth of damage per year. So you reach this stasis point in the trajectory. And for decades, this was just considered to be science fiction. It was completely dismissed. But now we actually have real longevity therapies that work. They don't work as well as we would like them to, but we have stem cells and blood products and senolytics and gene therapies and a host of other things that haven't even been discovered yet. So it is likely that this will be achievable in our lifetimes. So we at LEVF, why we're kind of uniquely positioned for this. If you don't know Aubrai, this is him. And he is world-renowned in our field and polarizing, I would say, but in a very good way. And so we, under his leadership, along with futurist David Wood, helping to guide our research objectives, we also, as a nonprofit, have somewhat of a hybrid model. I think that we benefit from being in this kind of middle space between academia and industry, because we don't have to deal with all the bureaucracy and whatnot, but we can still act with kind of startup speed. We have collaborations across the globe. As has been said a couple times today, silence is not siloed. We have a very limited amount of in-house expertise where we are the best at that thing. Everywhere else, somebody else is best at that thing. So we have people that we work with in 3 different continents and from multiple institutions, public and private, and we wouldn't be able to do it otherwise. Also, I think why excuse me, all of us are here, we are eager to, I guess, utilize this new, the crypto ecosystem to further our objectives. We've had this really interesting alignment, I guess, with the crypto world since, I don't know, 2018 maybe, excuse me, when Aubrey's been kind of tapped by players in the crypto industry several times. And I think there's broadly ideological alignment. People want to see things be done better because they can be, not just be satisfied with the status quo. So we are looking for ways to utilize new incentive models and engage with our stakeholders more so that the work that we're doing, which obviously is going to affect them, that they can have a say in this as well. We also are, we're built with the capacity to quickly respond to changes and get things done, as expediently as possible. We're in a hurry. RMR1 was launched really fast, faster than I would have liked, but really, really fast. And the next study is going to be much bigger and will also be done fast if the support is there. So now I get to the fun part. This is Aubrai, which was spoken about a bit earlier. And so one of the ways we talked about all these giant data sets that are being collected, and we talked about the corpus, I guess, of knowledge that it was trained on. Like everything that is in the presentation that I showed you, and quite frankly, everything that's in most of our new plans, I haven't fed to Aubrai specifically. However, he does reach largely the same conclusions or come up with the same suggestions for study design as Aubrai and I would end up with in conversation, which I think is a really good sign. I'm just going to show you guys what I mean, if this is going to let me. Yeah. Okay, so for example, for RMR2, this is the information. Oh, wait, it's not showing you. Uh-oh. Currently extending. Change. I want a mirror. Huh? What time is it? Okay, I have 1 minute. There we go. Okay. So this is essentially all that I gave it to start with and say, all right, what is it going to say? I didn't give it specifics about the interventions or anything yet. And this is a very typical Aubrai response. So doing power maths, which, Aubrai does the math in our organization, but also coming up with really important considerations about aspects of the study design. And I picked this part to just kind of show really quickly here, particularly because, so oxytocin, like the dosing and something, isn't something that I had decided on yet. A lot of times in the literature, they were doing, short pulses, sometimes 5 days, sometimes 12 days, sometimes 20 days. And so coming up with, okay, how do I want to implement this can be a challenge. And so it decided that it should be spurts of 5 days because of the cyclic nature, like the amplitude rises and falls over a 24-hour period, I guess. And so I was like, all right, well, if it's actually a problem, then give me information about this. And so it did, and then proceeded to build up a pilot cost estimate, which aligns pretty darn closely with our actual pilot estimates for what we've chosen to do. So this is, in one afternoon of playing with it, it saved probably at least a week of my life. And I expect that as these become, they're more finely tuned, they're trained on more data, and we're able to actually feed it steady results, and it's able to look at it and digest it and integrate that with the corpus of everything else that it's learned, we're going to be touching on things a lot faster than previously. So with that, I'm going to end. I'm over time. I apologize. I want you guys to get to ask good questions, but if you want to find me later, then I'm free to play with Aubrai. Yeah. Thank you.